You know, inside every graphics card, there's this secret war going on. And no, I'm not talking about frame rates or resolutions. This is something way more fundamental. It's a battle between just raw brute force power and really smart surgical efficiency. So let's dive into what's really happening under the hood. So you've probably heard this before, right? This comment kind of sums it up perfectly. The thinking is that asking a top-tier card, like a 5090, to be efficient is, well, it's like asking a giant pickup truck to be good on gas. It just doesn't happen. You want the best performance, you just have to accept the huge power bill and all that heat. That's the deal. Or is it?
But what if that's not the whole picture anymore? What if the engineers are, kind of changing the rules of the game? What if deep down in the silicon, there's a quiet revolution happening that lets these cards be both insanely powerful and incredibly smart about how they use that power?
All right, so this really gets to the core of the problem for any GPU designer. It's this constant battle, this tug of war, between giving us absolutely mind-blowing horsepower and then having to manage the fallout, which is always a ton of heat.
And let's be real, the horsepower is it's off the charts. We're talking about the next generation of top-end cards, like the 5090. And the word on the street is they are absolute powerhouses. I mean, built to handle 4K, maybe even 8K gaming, and barely break a sweat.
Okay, but here comes the reality check. All that power has a price tag. And I'm talking about the power draw. Some of these high-end compute GPUs, like AMD's MI250X, can have a TDP, that's thermal design power, of 560 watts. 560! To put that in perspective for you, that is literally like having a small microwave running non-stop inside your PC case. That is a ton of energy to deal with. So the big question is, how on earth do you tame that kind of beast?
Well, when you boil it down, there are basically two main ways to get this power under control. And this applies whether you're managing a huge data center or it's the hardware itself doing the work. You can either be proactive about it, or you can be reactive.
And the difference between these two strategies is everything. Let's start with frequency capping. Think of this as the proactive approach. It's like setting the cruise control in your car to exactly 60 miles per hour. That's it. It's predictable, it's steady. Then you have power capping. That's the reactive one. This is more like giving your car a fuel budget. Say, you can only use 1 gallon of gas per hour, and the car has to constantly speed up and slow down to make sure it doesn't go over that limit. It's more adaptive, yeah, but it's also a lot less consistent.
Now, this is where it gets really interesting. The research shows that in big, large-scale computing environments, that proactive approach, capping the frequency, is actually way more energy efficient. So why is that? Well, it's because it stops the GPU from making these little inefficient sprints up to super high frequencies. See, those high speeds need a lot more voltage, and that's where power consumption just explodes. By setting a smart, steady speed limit, you can get something like 13% more efficiency without losing any performance. That's a huge win.
But okay, these big system-level controls are really just one part of the story. The real magic, the really cool stuff, is happening deep inside the chip itself. You've got companies like NVIDIA building these incredibly sophisticated power-saving tools directly into their new architectures, like Blackwell. And what we're seeing is this whole arsenal of features designed to hunt down and eliminate wasted energy. We're talking about things like more precise clock gating, which is like turning off individual lights in a huge building. And then there's power gating, which is more like shutting off the power to an entire empty floor. Throw in super fast sleep states and the ability to change frequencies on the fly, and you got this really comprehensive strategy to boost efficiency.
Yeah, and this is a great way to think about the difference between those two big ones I just mentioned. Clock gating, that's like turning off the lights in a room when you leave. It saves a lot of power, but there's still a tiny bit of current leaking through, But power gating, that's the next level. That's like walking over and physically unplugging the lamp from the wall. You're cutting the power completely to anything that's not being used, so you get zero leakage. So what makes all of this possible? What's the secret sauce? It's speed. Pure, insane speed. The clock controller in Blackwell is supposedly over 1,000 times faster than the previous generation. It's making these power decisions in microseconds, not milliseconds. That's so fast that it can literally turn parts of the GPU on and off between individual tasks, and you, the user, would never ever notice a thing. It's just seamless.
Okay, so we've got the big system controls, and we've got the amazing innovations from the manufacturers. But there's actually a third player in this war for efficiency, and that person is you. There's a powerful technique you can use called undervolting.
So what is undervolting? It's actually pretty simple in concept. It's the process of figuring out the absolute lowest stable voltage that your specific GPU needs to hit a certain clock speed. And when you find that sweet spot, you can slash your power use and heat output all without losing any performance.
Now, it is super important not to get this mixed up with underclocking. They sound similar, but they're opposites. Underclocking means you lower the speed of your GPU, so it just runs slower, period. Undervolting is all about keeping the exact same speed, but using less electricity to do it. It's like tuning an engine to be more fuel efficient while keeping the exact same horsepower. Same speed, less power. So you might be wondering, why does this even work? Didn't the manufacturer set the right voltage? Well, it all comes down to something we call the silicon lottery. The thing is, no two silicon chips are created perfectly equal. So to be safe, manufacturers have to set a one-size-fits-all voltage that is guaranteed to work even on the absolute worst chip that comes off the assembly line. But the odds are pretty good that your chip is better than the worst one. It can do the same work with less voltage. Undervolting is just you, tuning your card to its own unique, perfect setting.
All right, so we've covered a lot of ground here. We've talked system controls, we've talked chip architecture, and we've talked about what you can do yourself. But what does all of this actually mean when you sit down to play a game? What's the real-world payoff for you?
Well, the payoff for gaming is kind of twofold. First, think about any time your GPU isn't running at 100%. Maybe you're playing an older game, or you've capped your frame rate. In those cases, all this new tech just slashes power consumption. Your card goes from guzzling power to just sipping it. But second, and this is the really cool part, in those super demanding brand new games, that efficiency turns into a weapon. All the power and heat you're saving gets reinvested back into performance. It lets the GPU hold higher, more stable boost clocks right when you need it most, giving you a smoother experience.
You know, when you put it all together, it really points to this fascinating shift in how GPUs are being designed. We might be getting to a place where the best graphics card isn't just the one with the most raw teraflops, but the one that uses its power the most intelligently. And that kind of leaves us with a big question to chew on. As these GPUs get smarter and smarter, will raw power start to matter less than intelligent efficiency? Is the future of performance not just about being more powerful, but about being a whole lot smarter?